I want to talk about how inertial sensors make movement an interface. They provide an interaction with intangible forces that lets you move beyond keyboards and buttons. And they can make embedded systems seem more human. They can make them seem more magical and integrate them into our lives. Personally, I think it's actually more magic if you know how the inertial sensors work. I work as an embedded consultant. I have clients and makers who come to me with an IMU in their system, and all they need is one accelerometer or a gyroscope. That's an awful expense if all you need is one thing. So my first goal is to help any of you in that boat demystify which sensors do what and how you can actually use them. My second goal is to give you some familiarity with the vocabulary associated with building a sensor fusion system, Kalman Filter, but don't worry about that word quite yet. And then you'll know what to ask for when you're buying an algorithm. And yes, this does add to more than 100%. Either I'm going to forget something, I'm going to run out of time, or they overlap a little. Speaking of math, there is going to be some math here. I know that not many of the sessions here have been quite this technical. If you like the equations on the slides, great. Understand them, follow them. If you don't, if you're not that bent, you're welcome to ignore them. They are not the most important part of the talk. I have some assumptions about the sensors you're going to be using in your systems. They are maybe an IMU. When we talk about 9 degrees of freedom, they probably have MEMS sensors in them. They're pretty cheap, they're tiny, they're reliable, they're pretty power efficient. I'm going to assume that your sensors are digital instead of analog. If you have analog sensors, you have to worry about ADCs and noise, and I don't have time for that. I'm also going to assume you're using 3-axis sensors, X, Y, Z, because it's a little simpler as I go through the talk. If you're using single-axis sensors, that's fine. It mostly applies, not all of it. You'll figure it out. These are the sensors associated with an inertial measurement unit, an IMU. When you talk about 9 degrees of freedom, you're talking about 3 axes on these 3 sensors, and you get 3 times 3 is 9. Accelerometers measure acceleration. Gyros are those sandwiches, and magnetometers measure X-Men powers. I fear that will be your takeaway, but I'm hoping I can do a little better. Accelerometers really do measure acceleration. And it's Newton's acceleration, F equals ma. Imagine we're in space and we're in 0G, we have free fall. How do you know if you're going a certain speed? You don't. You can't. Lots of physics says that. But you can tell if you're accelerating. And then once we know that we're accelerating, we get velocity by integrating. We can get position by integrating again. There is a little more to it than that, which we'll get to. However, I don't spend a lot of time in space, not nearly as much as I want to anyway. And that's why saying accelerometers measure acceleration is just as silly as all those other things. We measure the acceleration that is with us all the time, the acceleration that the Earth puts on us. We measure gravity. Sure, if you're in one of those spinny rides where you can walk on the walls, you measure that acceleration, and we call it centrifugal. But you also measure gravity. If you're spinning around in your car and zooming around, you measure that acceleration with an accelerometer, but you also measure gravity. For 90% of their lives, accelerometers tell you one thing: which way is down? So moving on to gyros, I brought a gyroscopic toy to explain this. How this has anything to do with gyros, I don't really know. It's got a spinning wheel, and that's what we think about when we think about gyros. Oops. Tops are gyros. It's what keeps them on their points, the gyroscopic stabilization, because they spin around. And when you have a gyro, you measure the direction it's not spinning because it provides a force. It pushes back against the spinning axis. The spinning axis wants to keep going in that direction. You get a force this way. And if you measure that force, you can find out how fast you're spinning. However, MEMS sensors are not gyroscopes. We call them that because they measure the same thing, the spinniness, the direction you're turning. But they provide no resisting force. They provide no gyroscopic stabilization. They aren't gyros. They're angular rate sensors. If you think about detecting spin, there's a good chance you're thinking about spinning around in your office chair. But any turn is spin. You think about waving hello. This is spin. If you think about waving hello this way, this is spin. Joints have spin. So think about it that way instead of the spinning around in a circle. Angular rate then is used to define gestures. And we can worry about the turns without worrying exact proportions and whether or not we're upside down when we wave hello. Because as humans, we don't care if we're waving this way or waving that way. It's the same gesture. I do want to pause before we go on to magnetometers and mention temperature. Because gyros, actually all of these sensors, they're MEMS sensors, micro-electrico-mechanical systems. And they're tiny. They change a lot with temperature because they are so tiny. They have no resistance to all the molecules going around. If you were building an airplane and you went from takeoff on the tarmac to cruising speed, your temperature shift would be so great that your gyro would spin due to an error. And what happens when your plane is told that it is spinning around? Well, if it's automatic, it tries to spin the other way, and since this is all temperature, now your plane really is spinning, and that's bad. So be careful of the temperature sensitivity of gyros. Moving on to magnetometers, where accelerometers tell you down, and from down you can figure out up, the z-axis. Magnetometers put you on Earth, and they give you an X or a Y, another axis, which is the Earth's magnetic field. They're not only prone to temperature problems, though. They tend to interact with magnets, they interact with metal, they interact with RF. So you want a Bluetooth magnetometer? You're gonna have to think about that one a little harder. RF, radio frequency, electromagnetic waves, think about the magnetometer and the magnetic waves. They're gonna fight. And yet we do this thing where many of you have iPhones, may already know how to calibrate some of these things out. The hard and soft iron calibration, you do this figure 8 thing, and now your phone can tell you which direction you're pointed. If you're gonna build a magnetometer in your system, think about the figure 8 thing or some other form of calibration so that you know what the nearby metal magnetic fields are doing to your sensor. So that's what each sensor does, in brief, and what you'd use it for. Do you have any questions before the quiz? I like that you didn't believe me that there would be a quiz. I actually have books to give away. I wrote a Riley book, so first 3 people to give me answers. To make a car driving arcade game where you are, driving, what sensor would you put in there? First person to say gyro. All right, come up, get a book. If I wanted to build smart block toys that would tell you which face is up. Accelerometer. Who wants to? Accelerometer, definitely. They know accelerometers know which way is up. They do gravity. I didn't see who answered, and I have 4 questions, so we're going to skip that one. Okay, come up, get it. What if I wanted to turn my screen on my smartwatch only when the user's looking at it? Gyro, yeah, exactly. An accelerometer has a place there, but the gyro is it's a gesture, it's a motion. And if I want to make an RGB LED, red, green, blue LED that would direct me home, that would be white if it was pointed north, and exactly. And I'm out of books and you all answered, so that was great. You passed the quiz. So now we get to go on to one of the fun things, and this is definitely an audience participation part. I'm going to teach you the inertial nerd handshake. It's a secret signal. And I do want everybody to practice. Since our agreed upon delusion known as geometry involves your right hand, we're going to work with the right hand rule, which means lefties blame physics and use your right hand. Your thumb is going to be up, and you're going to be pointed that way. Z is your thumb, Y is your pointer finger, and X is your middle finger. Y is going to go off to our left. And so this is sort of, I guess the left is that way for you guys. So this is the basics. Now, these two fingers don't do anything, and you can definitely put them up, but now I'm flipping everybody that way off. So that one's up to you. You can see, actually, when I do it on my own, I don't usually do the two fingers. However, since we are engineers and not physicists, because this is what physicists do in E&M class, and since we measure gravity most often, and we want that to be positive, the inertial nerd handshake or gang sign is this. And so we're going to go in the X direction. Now, Y is pointed to our elbow, often uncomfortably, and Z is down. Okay? Good. I have a little light box, speaking of RGB LEDs, telling you which direction goes what, that hopefully will illuminate some of these characteristics. Initially, there's a notes on it. I'm going to pass it around, but I will introduce it. You can see here it is blue, and that is because it is measuring Z. RGB and XYZ, they're sort of triplets, so red is X, and green is yellow or Y, and blue is Z. So this is the accelerometer mode. I turned it on, I pushed a button, it's in the accelerometer mode. If I turn it, it changes color. If I turn it again, it changes color again. If I move it, I don't know if you can see, it stays mostly blue. I can get into different colors, but sometimes it's kind of hard to see what color it is. Accelerometers, this is what they do. They quietly measure gravity all the time. They're kind of boring that way, but it's nice to have a nightlight. I'm going to push the button on top, and I'm going to switch it to gyro mode. Gyros are boring. Gyros are really boring, unless they're in motion, because they don't say anything unless they're moving. However, if I spin it, you can see now I'm spinning around the z-axis, and so it's blue again. If I spin it in a different direction, if I spin it around the x-axis, it's going to be red and green around here. And you can see how the joints are what's making a difference for the color. If you want to know, can I use a gyroscope to describe my gestures? Think about this. Can you describe the colors? You know, I want it to be blue and then green. So that would be a gesture you could put into software pretty easily. Push the button again on top. And this is North Star mode. It goes white, it goes dark when it's pointed south. Green is east, white is north, and red is west. So if somebody will come and pass this around, I'd really appreciate it. Button on top is off, and then in accelerometer mode now. If it is a bit of a hack, you can see all the electronics on the top, and if it breaks, just bring it back. I'll power cycle it. The button on top changes the mode, yeah. And there is a little post-it that describes the different modes and what you should expect. After all that, inertial measurement units aren't just accelerometers, gyros, and magnetometers. The sensors can work together to create more information. Orientation or attitude values like roll, pitch, and yaw are pretty straightforward. We'll see that trigonometry in a few minutes. However, navigation values are a bit trickier. Unfortunately, those algorithms are postgraduate level math and pretty far outside the scope of being able to implement it when you're done here. I want to give you the terms so you can buy the right one. So let's start again with accelerometers. We saw this before. Imagine we're space, acceleration leads to velocity, velocity leads to position, but that's not right. It's just not that simple. In calculus, if you remember, when you integrate something, you have a plus c, and we ignore that when we're dealing with just equations. But in the real world, we have to deal with the plus c because what it represents is our initial conditions. If we could stopped, totally stopped, and then accelerate up, we might be able to use these equations, assuming there aren't many errors. And yet, there will be errors. Vibration is a huge error. Temperature. But the big problem is, again, that we're not in space. The constant source of acceleration that is our Earth means that just using the accelerometers to determine this orientation and determine speed and position isn't likely to work. How do you know which forces are due to gravity and which are due to you zooming around? If you aren't in space, you have to take gravity out to get velocity. And it's not that easy. Gravity is 9.8 meters per second squared. A 1 degree, one tiny degree, I can't even show you 1 degree, it's like 10 degrees. One tiny degree in getting that wrong and getting the direction of down wrong puts a leak into your integration. And it's a 0.17 meter per second squared leak. It doesn't mean much, except that after 60 seconds, you're 10 meters per second off in velocity. That means we traveled through this room in 1 second, or it means you're 22 miles an hour off. You're also, after 60 seconds, with that tiny 1 degree error, you're talking about 3 football fields away from where you think you are. That plus C really makes a difference. That error really builds up quickly. What do? Well, the answer, strangely enough, is we add a gyro. To give you some intuition, I want to kidnap you and blindfold you. It's a thought experiment only, of course. You are tied to this relatively plush chair inside my spiffy getaway car. And let's say you just have an accelerometer and to measure things. Sure, you know when you're speeding up, you know when you're slowing down, but telling the difference between a slight incline and speeding up is pretty difficult. It gets tricky, and what if you're in a cloverleaf where you're getting on the freeway? Well, they get pretty fooled. Accelerometers get very fooled in constant acceleration, things like that, in banked turns. They don't know whether or not you're accelerating down from gravity, accelerating forward along your heading because you're zooming, or accelerating through the banked turn because of centrifugal forces. Any prolonged acceleration, the gyros get confused. They think it's gravity. Oddly, that may be hard for you to really get your head around mentally because you have a really good gyro and a really good accelerometer in your head, and you already know how to put them together. If you were in a car, even blindfolded, and your ears plugged, you'd know if it was moving between the vibration and the spinning. Cloverleafs wouldn't confuse you much. They might initially, but you're used to that motion. And you're really good at differentiating the direction of gravity because it's really important to humans. You know which sensors bring which errors. And so you use the sensor you can trust, and you don't use the sensor you can't trust. You can tell when your kidnappers turn around a corner, when they yaw. You can tell when they pitch up and down hills or roll in the car. And I should stop there and really define those terms. I'm going to go back to using my inertial nerd handshake. We have X is that finger, Y, and Z. When we turn around a corner, when we do yaw, we're going around the Z-axis. When we pitch up and down hills, we're going around the Y-axis. And when we roll, which is usually bad in a car, we're going around the Z-axis because we're always traveling in the Z-axis. So if you're turning around the Z-axis, that's roll. Together, roll, pitch, and yaw form orientation or attitude or Euler angles. And Euler angles are probably the one that are the most confusing to see because it's E-U-L-E-R, the mathematician Euler, not the hockey team. If you use the accelerometers and gyros together, especially with a thing like a Kalman filter, you get your Euler angles and you know your orientation. But can you tell where you are? If you're kidnapped and blindfolded, you know where on earth you've gone. With an accelerometer and a gyro, maybe if you're home and you know the area really well, and also if you know where you started. And that brings us back to those initial conditions. your inertial system also needs to know where you started in order to have a chance. Even if you assume that the kidnappers stick to roadways, you have to know where you start from in order to use that to get away, in order to escape, which of course is our goal. The accelerometers and the gyros are too imprecise to be integrated on their own without the errors building up to catastrophic levels. On the other hand, they have some of the same information, which means they can be used to get rid of each other's errors. Acceleration, to get position, you can double integrate acceleration, just a different way than it showed earlier. Assuming you're willing to deal with the numerical integration errors in software and the initial conditions and vibration and temperature and all that. You can get a very similar measurement, the position, from the gyros by doing a single integration. Same stuff, you still need to know the initial conditions. They have a different set of errors, and they're very vibration sensitive. But your two calculations of position here are gonna be different. They're gonna be pretty different. Which one do you trust? Under which conditions do you trust them? Back to our kidnappers. If you get conked in the head in this whole process, and you feel sort of dizzy, you know that you aren't moving. That's a dizziness you can discount because the car hasn't accelerated, it isn't vibrating at all. You trust your internal accelerometer of your gyro. But if you're on that clover leaf, you know that your accelerometer is dealing with the the centrifugal forces. So you trust your gyro. You have a model of how the world works. And under specific conditions, you estimate there's more error to be had in one sensor or another. Now, if you had a magnetometer, imagine a magnetometer is like a flashlight that constantly points at you from one direction. No matter how you move your head, it just points at you. It's stationary, but it gives you a lot more information about where you are and which direction you're pointed. Now, even with integrating, you probably don't know where your position is if you don't know where you start, but you have a lot more information about which roadway you might be using. And then you'll be able to lead the police back to the hideout for the kidnappers, which wasn't me, by the way, of course. Turning all that intuition into software is the tricky part. The whole calculate position two different ways and who has more error under which conditions leads us to an algorithm called the Kalman Filter. It's a big topic. I'm going to see how much I can do, having totally lost track of how much time I have. The goal of the Kalman is to give you an answer, an estimate of what the real world is doing. There is if you search on Wikipedia at the bottom, you can get to a nice description of this. The goal of the Kalman is to give you an estimate of the real world, say roll, pitch, and yaw, the Euler angles. And it might also give you velocity, it might give you position, it might give you altitude. The secret way the Kalman does this is by combining a model of how things should be with a measurement from somewhat unreliable sensors. The key here is the error estimations. It estimates what's really happening based on those measurements and what it thinks should happen, what it predicts should happen. And then it uses those measurements to correct your predictions as well as give you an update. So your measurements feed into your error estimates and they feed into your answer. And then the Kalman does it all again. The prediction and error estimation depends on what's happening. If you're moving, as we were talking about, the gyros kind of know what's going on. If you're stopped, the accelerometers kind of know what's going on. If you're not sure, maybe the magnetometer can tell you which one is more correct right now. But these are all models. They fall under the prior state of knowledge, how things work. And the measurements are what your sensor is giving. The output is what you want to know, but it feeds back into the error estimates and model of the system. So you're using the sensors to tell if you're stopped or moving, and you're using them to tell all this other stuff. It's very chicken and eggy. Am I here or am I there? But that's what the Kalman's good at, actually. However, it's pretty mathy. It's the sort of algorithm that will put you on a Cortex M something and keep you off of an 8-bit Arduino. That's what I do during my normal job. So I'm not going to talk about processors too much. In the Kalman, you can add additional pieces of information. It's not just accelerometers and gyros and magnetometer. You can add whatever information you have. If I have something that will tell me the wheel speed of the car, think about how knowing the actual true velocity will help me improve my accelerometers, because then I will know when they're lying to me, and I'll be able to tweak them. I'll be able to estimate their errors better. And if you add GPS, which is a really exciting, common thing to do with inertial sensors, GPS updates every second. But what if you need to know a lot faster than that exactly where you are? Or GPS only tells you where you are. It doesn't tell you how you're oriented where you are. And so the inertial sensors can work together to get much, much more accuracy than working just alone. Whatever sensors you have, you combine them and do the fusion solution. Sadly, tuning a Kalman is sort of magic. It depends on what type of vehicle. I've been talking about cars. They are limited to a 2D solution on a very bumpy earth. Maybe you could be on a mountain, maybe you can be in a valley, but you have to be on the surface of the earth. Boats, on the other hand, get a lot more tossing and turning, but their average altitude is sea level. And spaceships, which is down here somewhere, spaceships don't have any gravity to get rid of, so they're different. These are all big tuning knobs on a Kalman filter. And so you need to know what you're going to go into, and you need to know what your sensors are doing. But there are a lot more knobs to tune on that filter, like how much temperature is going to get through my temperature calibration. So I shouldn't trust this under that condition. And how sensitive is this particular sensor to vibration, and how much vibration am I going to see? Those are the smaller things. You really have to understand the environment you're going into. It's very much garbage in, garbage out. Crummy sensors into a Kalman filter won't make them perfect. It might make them a little better if they're matched with crummy sensors in a different way. And that's why you match accelerometers with gyros. They're crummy sensors, but in two entirely different ways. Don't tell your Kalman it should trust a sensor that's particularly bad under the bad conditions. And you don't need a Kalman filter for everything. As I noted in the beginning, the sensors are very useful on their own for doing what they do. You should stick to sensor fusion when you really need it. You don't need a full Kalman algorithm if you need to handle portrait or landscape, or if you're doing step counting, or even basic gesture recognition. Kalmans are about position and velocity and precision. And I can't cover it all, so I'm going to stop there with Kalmans. The books with the yellow stars are the ones that I personally prefer, especially if you have insomnia. The blue one there, Quaternions and rotation sequences, isn't even really a Kalman filter book. But it's probably my favorite, and it reminds me that I need to talk about Quaternions. This is the sort of thing that mathematicians do just to dork with engineers. Okay, so we have our x, y, z vector, right? And it's roll, pitch, and yaw. But you want to go all the way around in a circle. You want to go all the way around, minus pi to pi, or 0 to 2 pi, or if you don't want to use radians, 0 to 360. And so you want to go all the way around the circle, which is no problem. It's a very analog thing to do. But in the math, you get to 359.99. And then you move just a little bit more, and suddenly you're all the way back over to 0. Math doesn't like that sort of discontinuity. And that's what the Quaternion is for. It's not some secret, horrible, scary thing. What it does is put everything into the fourth dimension and let you do your math there, not time, a different fourth dimension. And it takes away the discontinuities. You can use sines and cosines to get from the Euler angles, the roll, pitch, and yaw, from 3 space to the Quaternion 4 space. You do all your Kalman and movement math on the Quaternion, and you don't have any discontinuities. Of course, this isn't exactly for the faint of heart or fearful of trigonometry. It will likely give you a headache, and it will keep you off fixed point processors. And you do still have to do the reverse computation, which is even messier. But it saves you from those strange discontinuities that cause problems. And I don't want to give you the wrong idea. The Kalman Filter and Quaternions are not where the messy math starts. The messy math starts as soon as you pick up an inertial unit. Let's go back to magnetometer and think about calculating heading. I've been talking about yaw, but heading is the direction you're pointed with respect to magnetic north on Earth. Heading in space doesn't mean anything. So, and yaw is turning around. It's a relative. You turn right, that's a yaw thing. You go north, that's a heading thing. There's another word that might come up, and that's bearing. Heading is the direction you're pointed. Bearing is the direction you're traveling. In a car, for the most part, they're the same. But if you're screeching around a corner, you might be drifting out, and that would mean your bearing is a different direction than your heading. More important in airplanes where wind can push you around. The magnetometer can be used to calculate heading. The first part, it starts with case sensor X. It's not really important that you read the code. Before we get to the trig, the question is, what angle are you measuring with respect to? And this is a big, important part of inertial systems. The sensor doesn't know what the system is doing. The sensor only knows what the sensor is doing. And so those of you who have gotten to play with the inertial North Star gadget, maybe you noticed that just because it was pointed north didn't mean you were pointed north. You need to make sure that your system and your sensors are aligned. And they don't have to be perfectly aligned. The body frame of your system and your sensors just have to be aligned in a way that you can get between them using math or orientation matrices. And that makes me think about a time I worked at Crossbow, which made inertial measurement units. We sent out 2 units to a famous car magazine, and they sent us data that was terrible back. But I knew that it was good because it had sat in my car for 2 weeks. I'd had lots of fun with playing with it. And we sent out our QI guy, but I was on the next flight because these were really important people. And he called me like minutes after he landed. And he said, "No, I'll send you good data tonight." What they had done was they had put their inertial unit, about the size of the box that's being passed around, inside the car. And then they'd driven around closed course professional drivers. And Walter got there and he bolted it down for them. Sort of important. So back to the math. The first snippet is the trig you need if you're calculating heading using magnetometers. That's sort of a bad idea. Remember how if we got our tilt wrong with the accelerometers, we leaked errors into our position? If you get your tilt wrong on your magnetometer, you leak errors into your heading. Even if you're using 3-axis magnetometer, tilt compensating them really helps. And so don't just use this arctangent. Go down to the big math on the bottom. It's a more complex formula, but you use the accelerometers to tell you how your vehicle sensor is oriented, and then you can find the heading from there. That was a crummy format. Let's try again with real math. If you read the whole heading calculation, it's pretty complicated. Trigonometry is your friend. Sorry. I know it hasn't spoken to you since high school. But mostly code written by other people is your friend. Adafruit did a really, really good job with their 9 degrees of freedom sensor fusion code. It's very well explained. So the bottom one is heading, H. And you can see how it depends on MX and MY and MZ. But it also depends on roll and pitch, which were calculated using the accelerometers on the top. This is so common that most magnetometers are now coming with accelerometers. Of course, you do still have to do the math yourself. Oh, that's the wrong way. But that's enough math. The short answer is to hire smart boffins to do the trig for you and to buy navigation. Still, things can go wrong. I mentioned about gyros being temperature sensitive and all of the sensors being temperature sensitive. That's true across the board. But A related point is that these sensors are mechanical. MEMS, microelectromechanical systems, the mechanical sort of important. They're very complex. The sensors may react strangely, which is to say non-ideally, in all sorts of physical environments. Sure, you have to bolt down your sensor, but stress and strain can cause a problem, so don't tighten those bolts too much. Vibration. Well, if you're an accelerometer, vibration, causes what you'd expect. It goes up and down and up and down. If it doesn't sample fast enough, it can be a problem. But there are some vibrations for all of these sensors. They just don't function anymore. It's not a matter of accumulating error. It's just broken. RF makes sense that the magnetometers might not work, but some gyros are sensitive to RF too. And strangely, light. Some of these sensors are sensitive to light, which is just weird. Cheap MEMS sensors may be the only economical way to get a product on market, but you're going to have to be real-world engineers and do real-world testing, get the environmental testing done pretty early. And note that these all contribute to errors in the output. They all contribute to errors in the Kalman filter. Temperature can be calibrated out if you're willing to pay for it in manufacturing, but some of these are intrinsic to your environment. So if you're going to go talk to sensor vendors, what do you ask them? Bandwidth is probably the first thing. How fast are you measuring the signal? How fast can you measure what's happening? 100 hertz is a decent place to start. If you're talking about human things happening, if you're talking about interacting with gestures, or you're talking about going into cars and zooming around, as long as you're not doing NASCAR level stuff, which was fun, you can do 100 hertz. If you're going to do VR, you're talking about 250 hertz, because we do not like it when the external gyro and our internal gyro don't work. That's where all the vomiting comes up with virtual reality. That's bad. Another thing you want to talk to the sensor vendors about is synchronous sampling. You think about this gesture with the smartwatch turning on gesture. If you measure the accelerometer now, and then you measure the gyro now, and then you measure magnetometer now, they did not get the same measurement. They were not in the same spot. They were not doing the same thing. So your goal is to measure now, poof. Even if you can't measure as fast as you want to, that synchronicity will help you measure the same thing across the different sensors. There are ways to mitigate that. If you can't do it, like an Android phone won't let you do that. But they're a pain, so I'm not going to go into them. I mentioned mounting, and I'm almost out of time. I mentioned mounting. Don't forget that you have to mount the sensors with respect to each other. Your accelerometer and your gyro and your magnetometer, if they're not in the same package, they may not be exactly in the same space. So do you care about that level of precision? If you do, we're back to talking about calibration in manufacturing. Every time I say calibration, you should be like doubling the price of your product. Because if you have to calibrate, it gets really expensive quickly, whether it's temperature or misalignment calibration. The whole manufacturing process is something you should start thinking about early in the development process, not just, is it a whizzy sensor? And the sensors have to be accurate or precise. Well, if you're willing to calibrate, cha-ching, then you can have precise and not accurate. I've talked a lot about accelerometers, magnetometers, and gyros. I want to recap my algorithms, give you a few more. Barometers are one sensor I haven't talked about. If you look for inertial measurement units, you see the 9 degrees of freedom, and then you're tempted by the 10 degrees of freedom because 10 is better. That 10th one is usually a barometer, an air pressure sensor. It is for short-term relative motion. It doesn't tell you, oh, I'm so high, the air pressure is so low, I must be on Everest, or it's the other way and I must be in Death Valley. Because weather impacts the air pressure, you can't rely on it to that extent. Instead, you take it now in order to see if it's going to change over the next minute or two. If you have a Fitbit and it's one of the ones that tracks stairs, they use a barometer to check when you're going upstairs, but they only take the measurement when you're taking steps. And that's how they get around worrying about weather. Barometers are usually accurate to 3 inches. I mean, it's pretty good. It's just kind of strangely good. I didn't realize the air pressure at my feet and my head is so different. This isn't the idea of taking the barometer measurements only when you're moving isn't a Kalman filter, but it is an example of only taking the measurement when you can trust this data. It could be fed into a Kalman filter, give it a little bit more information, or if you're in an airplane and you want to know your altitude, that's a lot more information. This slide was out of date the minute I made it, and now it's been a couple of weeks, so it's really out of date. I did limit it to things that you can get on Adafruit on boards, which does also make it more out of date. But you get an idea. Accelerometers are usually cheap, cheaper than gyros anyway. Magnetometers, the inertial measurement units as a whole, $20 is cheap. Why, in my day at Crossbow 15 years ago, it was $2,000. They're 2 to 5% of what they were 15 years ago. And it's amazing. They're better too. Better temperature stability, better bias stability, better noise. And they keep getting better. This is an area that is quickly growing because they either get better or they get cheaper. And right now they're still doing both. If you look at them from a power perspective, it sort of tracks the price, strangely enough. Accelerometers are usually lower power than gyros. Magnetometers are also low power. And so if you talk about doing this gesture, you might want to leave the gyro off until the accelerometer says you're moving. That last one, the MPU, is from InvenSense. They have a navigation solution available for licensing. They're one of the few. I don't have a particular favorite. I can say that that isn't my favorite, but I don't have a better one, so that's all I've got to offer. They do come out with new ones all the time, both IMUs, sensors, and navigation algorithms. So keep an eye on what's out there. While you think of questions, I am going to do my acknowledgments. Thank you to Tony Rios at Crossbow, then Memsic for teaching me most of what I know about this subject. Thank you to Walter Stockwell for saving me a trip out there. He was at Crossbow and now he's at Trimble, and he reviewed my slides and added some numbers, which I thought were pretty cool. Anything I got wrong was purely me. Anything I got right was at least partially them. I'm Elecia White. I wrote a book. I have a podcast where every week we talk to people about building their gadgets. I have stickers if you want to remember the podcast, so just come get them. We have over 100 episodes talking from everybody from other mill to Kickstarters to processor vendors. It's fun. Okay, questions? And please wave your hand because I can't see you at all. Yes?
How do you deal with slip when you're looking at wheel velocity or other kinds of things with inertial sensors?
How do you deal with slip?
Yeah.
So
I guess the example would be you might have a way of measuring your wheel velocity, but if you're going around a curve, like a figure-eight ramp, you're slipping all the time, so your wheel velocity isn't representative of your forward direction. Your accelerometer is confused, and your gyro may or may not be telling you anything useful.
okay, so going back to using your own internal measurements, you get an accelerometer. If you were, slipping around a corner, you were skidding. Your accelerometer does something weird there where it turns out the back. Your gyro is telling you you're spinning around. And your wheels then, your wheel velocity, your slip, wouldn't be fed in. Now, can you put that in software? Yes, because that sideways acceleration is really strange in a vehicle. In planes, it's a little harder because wind causes slip, and that isn't something you feel as strongly. So, yes, you could tell in a car, right? If you did it, then you probably can tell in a Kalman filter. Yes? Towards the back? No, never mind. Any other questions? Yes?
You can't hold these sensors onto the body. Is there anything to consider that level of complexity?
Yes, because wearables are where it's at. So, you see a lot of wrist-mounted things, and that's sort of tough because if you want to fake out your pedometer, you put it on your wrist and then you hold a shopping cart. Because now it's not moving. You can't tell that you're moving very well. That's an example of not measuring what you want to measure. Because what you want to measure is basically your hips moving. How do you do that? I sort of miss my little Pocket Pal Fitbit. I thought those were the best ones. But more wearables are doing adhesives if you're doing long-term measurements. That's one way. I look forward to when we actually get tattoo circuits. I think that will be a lot better. That's sort of bolting. There isn't a good method. Neck-based and ear-based computing are two areas that I think are going to allow inertial sensors to be more body aware. Yes?
So when you start sticking things on your neck, how do you figure
I totally need a dance move for that.
Can you do calibration without figure weight? Can you do it more along the sort of ways you can calibrate?
You can. The very simplest calibration is to just spin in a circle. Your goal here is that you're showing the magnetometer all of the different values it can get. And so if you just spin in a circle, you're showing it 2D worth of values. If you do the figure 8, you're showing it 3D worth of values. And so I can imagine if you put it on your head, you spun in a circle, and then you did this. That would actually give you a pretty good view of the magnetic field around you and let you compute soft iron calibration. And what you do there is you look at what's out there, and then you try to fit it to a circle, and whatever differences you have from the circle are the... I'm really doing a bad job of this. This requires a whiteboard. It fits to the circle, and that's the calibration values you use to know what's local and what's offset. I'd be happy to talk about that more, but I think I do need paper. Dan.
How thorough are the data sheets in terms of allowing you to compensate for temperature? I know some of the sensors I've worked with have gotten the temperature data output on one of the pins. How useful is the data sheet in helping you use that data to compensate for the values that you're getting out? Are they generally good?
If they have that data, they're generally good. A lot of sensors don't come with that data or come with a pretty big error margin. The MEMS group, which is an industry group, MEMS industry group, actually has done a lot of work with getting the data sheets formulaic, so you can compare accelerometer to accelerometer outside vendors. And that has been really, really helpful. They focus on digital sensors and not analog. But yeah, if it comes with a temperature calculation, use it, because they've already done your calibration for you. It won't be as good as when you do it in the system, but it depends on whether you want 1 degree of accuracy or 0.0001 degree of accuracy.
Is it common to put an external temperature sensor or a third-party temperature sensor into your design?
Sometimes. The gyros and accelerometers often come with internal temperature sensors. You should use those if you have them. If you don't have them, then a temperature sensor nearby is good. You don't really care what the temperature outside is, so you don't need that. And I mentioned the 10 degree of freedom inertial measurement units. Sometimes that 10th is temperature instead of barometer. I think that's cheating. I think everything should come with a temperature sensor. Okay, thank you. If you want a sticker, please come up.